is Visionary, a show exploring how nuclear powers your world. I'm Mary Carpenter.
And I'm Jordan Houghton. Let's jump in.
Hey everyone, welcome back to Visionary. And hey Jordan.
Hey Mary, welcome Visionaries. We're thrilled to have you back for another episode.
Yeah, today's a great episode because we're revisiting a topic we first explored back in season 2, and it's nuclear in space. Space exploration is pushing the boundaries of what nuclear can do, from powering deep space missions to sustaining long-term human presence on the moon and Mars. And what's really exciting is how these advancements don't just impact space travel. They're shaping the future of nuclear energy here on Earth, too.
Yeah, when we spoke with NASA's Trudy Cortez back in season 2, and listeners, if you haven't heard that episode yet, it's a great time to go back and give it a listen because it ties in really nicely with today's interview with David Poston of SpaceNukes. But Trudy walked us through some of the advancements being made to get nuclear reactors into space, ensuring astronauts and spacecraft have reliable power. And she gave us a look at Krusty, which was a project that today's guest also worked on that has an incredible tie-in to the Simpsons, which we'll talk about a little bit more in the interview, which proved that small fission reactors could be a game changer for missions to the moon, Mars, and even beyond.
Yeah, the success of Krusty's experiment back in 2018 set the stage for even bigger projects like NASA's Fission Surface Power Program, which is aiming to put a working nuclear power system on the moon in the late 2020s, which is not far away.
I know. It's like all of this seemed like Star Trek, like way out in the future, but a lot of this is coming to fruition in the next decade. And it's like the future is now.
Yeah. I mean, we recorded this episode just a couple weeks after Katy Perry and that crew went to space. I mean, it's really happening. People are going on space tourism rides.
Yes.
It's the Jetsons. I just hope that we have flying cars to avoid traffic. And I don't know if you watched the Jetsons, Jordan, but the mom had the system where she could just sit in the chair and ride through, and it would like do her hair and her makeup and pick out her outfit. Space is cool, but that's also what I'm looking for.
I know. I feel like the men all want the hoverboards from Back to the Future, but yes, I want the robotic hair and makeup.
Yeah.
So I think what's really interesting about the fission reactors is what we're talking about today with SpaceNukes. But SpaceNukes is one of several companies partnering with NASA on fission reactors and fission technology in space. And also, and we're not covering this in this episode, but talking about NASA's turn back to looking at nuclear propulsion. And the thing that I think is so cool about this is NASA turned away from nuclear for a really long time. And now these collaborations with companies like SpaceNukes and Kilopower are really showing how NASA's coming back to nuclear and seeing it as a reliable source of energy, a reliable source of power, and a reliable source of propulsion that other technologies can't offer.
Yeah, there's so many interesting ideas and concepts out there that are starting to come to life. Like you mentioned, Kilopower, their nuclear batteries are designed to help survive the lunar night. So they basically enable missions to operate for years instead of weeks on the moon and provide the heat and electricity needed to survive the extreme cold and darkness. So there's a lot of these exciting projects going on, and we'll dive into one of those today.
Joining us today is Dr. David Poston, a leading nuclear engineer with more than 30 years of experience designing reactors for space exploration and beyond. As the chief reactor designer for NASA's Kilopower project at Los Alamos National Laboratory, he played a key role in groundbreaking tests like DUFF and Krusty. Can't wait to talk more about those in a little bit. From deep space missions to advanced reactor concepts for defense and commercial use, Dr. Poston has been at the forefront of shaping the future of nuclear technology. Welcome to the podcast. We're really excited to talk to you. I would love if you could start by telling us a little bit more about yourself and specifically what got you interested in working in the world of space exploration.
Well, I started like a lot of people my age, like in the Apollo area. I was a big sci-fi fan. I was a member of the sci-fi book club and got books every week and read Asimov and Bradbury and all the old classics. And
So this is like when you're a kid.
yes, and
Okay.
this is when I was a kid. Yes.
So you've always known exactly where you want to be.
Well, I always knew space, right? And so that was the easy part. And when I went to get a master's degree in mechanical engineering, then I got a job with General Electric nuclear energy, because then I thought nuclear is really cool, right? And then that was when the marriage kind of happened. I worked on a project called SP100, which was a project to put power in space, nuclear power in space. And I said, this is the greatest thing ever. And I wanted to go work on it for my career. So I decided to get a PhD and go to Los Alamos National Laboratory, because that's where they did all this. So I've spent about 25 years at Los Alamos. And despite all the good pictures you see and everything, not that much has gotten done. And that's why we did Duff and Krusty. And after a while at Los Alamos, I left to me and the guys that did Duff and Krusty formed a company called Space Nuclear Power Corporation, or SpaceNukes. And that's where we're at today.
Awesome. Well, I'm glad. It sounds like you're a book fan. Keep that in mind, because we're going to have a question for you about books at the end of the episode. So our audience got an introduction to the role nuclear can play in space travel in season 2, but we'd love to hear more from you about your perspective. How crucial is nuclear fission for powering long-term human exploration on Mars?
Humans are very ingenious, right? We find ways to make things work. But if we want to do anything substantial, it's 99% essential. We won't be able to do any significant exploration or extended stays or build a colony on Mars or the moon without nuclear power. We've got the physics down. It's the engineering we have to get done. So solar power is really good at the Earth, especially in Earth orbit. But as you get further away from the sun, with the radius squared, the power level goes down. So Mars is quite a bit further away, so the power is a lot weaker. But that's not the big problem. The big problem is really trying to deploy large solar arrays and in dust storms and dust covering the arrays. Because if you saw The Martian, the dust storm was a big problem, right? And I hate to say it, that movie was awesome, but it way underestimated how many solar panels he'd need. He was driving around in his rover, and he had like just a little thing to put on top of his truck, and it would have been like 100 times more he needed. But it's really its ability. It gets very cold, and all the dust storms that the solar panels, you would need football fields of solar panels just to get the amount of power that he had in that rover. And so that's nuclear is something we can launch and land and be compacted, and we don't have to worry about the eclipse of the sun at night. So it really works really well.
I'm glad you mentioned The Martian, because I was going to interrupt and tell you that if we're talking about Mars, I personally am thinking in terms of The Martian. That's like the extent of my Mars knowledge. So talking in terms of The Martian like puts it all into context really well for me personally.
It was really well done. And he had his plutonium-238 source for heat, which made sense. They'd been buried there before. And they had their ascent vehicle that they were refueling to leave, which all of it was really great, except the amount of solar panels you would need to do what he was doing would have been like 100 times more if you do the calculations.
Can you break down a little bit further how the dust storms play into this and why you need so much energy to survive the dust storms?
It's really solar panels won't work very well. Right?
Oh, I see.
It's because they cover up the sun. It's not like you get zero sunlight, but you would need about 10 times as much solar panels to survive through a dust storm as you would without a dust storm. And the dust storms last months. Right? There have been some that cover the whole planet for months. And so if you're going to survive that, the solar panels aren't going to get you there unless you just have a crazy amount.
Let's back up, because you're at SpaceNukes now, but let's go back a little bit to Krusty and Duff from Los Alamos. And we actually brought this up when we had Trudy Cordes from NASA on in season 2, just briefly, because I mentioned that prior to being at NEI, I was at the Atomic Testing Museum in Las Vegas, and we actually had your colleague Pat come do a lecture at the museum and talk about Krusty when y'all were testing it on the Nevada National Security Site. So I got like really hyped about Krusty. We didn't talk about it a lot with Trudy, but since we have you, I would love you to talk a little bit more about those projects, where they came from and how all of the testing went and what's next.
Yeah, no, that's a great question. And they really came from the result of a failed career in a failed nuclear infrastructure in total. Me and Pat were sitting around kind of lamenting how hard it was to get things done and that nothing's really been accomplished in our careers because the United States hadn't built and tested a new reactor, since the last one was like in the early 70s, which is just astounding, right? You hear all the stuff about the nuclear renaissance, but we still haven't, right? And so we wanted to see what can we do that could be of interest to NASA as easy and cheap as possible. And so that was DUFF. DUFF was the demonstration using flat top fissions, which was used kind of an existing reactor, existing Stirling engines, but did make electricity with a Stirling engine with the heat pipe in the core. And we brought a bunch of NASA people to that test, and they got excited. Maybe we can do nuclear, because NASA had given up on nuclear. The world had pretty much given up on nuclear at that point. And so we went ahead and convinced them to do Krusty, which was designing, building, and testing a whole reactor power system. And it worked extremely well. And a lot of it has to do with how we designed it and how simple it is as a nuclear reactor, which is one of the reasons it worked.
And how about DUFF?
Oh, DUFF was the first one.
And can you share how you came up with these names for these projects?
Yeah. First, our company name, the SpaceNukes, is a little controversial, right? Because you're putting space and nuke out there. But that kind of shows that we're, you either have to like sit back and play the game or kind of try to be a disruptor. So I guess I would call us more of the disruptive side. But the Simpsons names go back a long time. Pretty much every project I'd worked on, I'd had a Simpsons reactor character as a name. And so the first one was Homer. But then when it came to DUFF, I was always looking for Simpsons acronyms. And what was funny was when we proposed Krusty to NASA, there was this huge kickoff meeting with probably 60 to 100 people there. And some big NASA executive said, "We're not naming our reactor after a drunk cigarette smoking clown." He actually said this, and everyone kind of looked scared and everything. But it turned out we'd already filed the official paperwork for the project. It was named Krusty, so we got away with it. And in the end, everyone loves it. I mean, you get used to just calling it Krusty at a project level. But when people did media reports, they show little clips of Krusty the Clown and Duff Beer, and I think it was more engaging. And so I'm glad we did it, and I think it still pays off. It took to not take things quite so seriously and focus on what matters.
We've talked about The Simpsons several times on this podcast, and it's usually in the context of how the show has created some wrong impressions around nuclear. And so it's great to have Simpsons-related names tied to something positive and successful.
Yeah.
Well, it's funny. That's the problem. We look at The Simpsons as so misrepresentative that it's funny, right? I mean, because it is. It's a parody of nuclear. But I guess if people take that seriously, that's kind of scary, right? I mean, it's just
it's a cartoon.
My show would have to educate better if people think the three-headed fish are coming out and carrying plutonium in your pocket and all that stuff.
So Krusty was successful. Then what?
So Krusty was successful, and afterwards, the head of the NASA Science and Technology Division announced 3 times in conferences and press events they were going to fly Krusty, fly the Kilopower reactor. And so, we were on cloud nine. And then a new NASA group came in, and there's a long story about politics, but politics always have a play in everything, right? I mean, the politics not as in like the U.S. government, more just, who, what, and where kind of politics. And they decided to go back to the old model of like playing in the sandbox, as we'll call it, where people will propose cool ideas and they'll try to work on technologies for them. But, we call them PowerPoint reactors or paper reactors. So it kind of went in that direction. I don't know if you're familiar with Admiral Rickover. He did the naval reactors back in the 60s and 70s. But he kind of saw this coming. He called them academic reactors. But there's so many people that propose these great reactors, but they don't really know what a real reactor is in terms of a new reactor especially. We have that going on a lot right now. But that cost us, at Los Alamos, they decided they were going to stick with that big kind of like safe infrastructure of all the national labs, all the DOE getting together and agreeing on the same thing. And we didn't want to do that. We wanted to continue to build and test and fly. And so we left the laboratory and founded our company and trying to do that privately, still mostly through government projects, but we do have some venture capital potential. And so we're trying to do it, keep it simple, get something in space. We're looking for the Sputnik moment, right, for what you would call it for space reactors, because nobody really takes reactors in space seriously until we're operating one. And so that's what we want to get done. And we have the technology ready. We just have to convince somebody to put it on a rocket and go.
You should have sent one up with Katy Perry last week.
Yeah, I was going to ask you your thoughts on that.
Yeah, that's funny. Yeah, that's good.
Why Mars? Why are you guys focused on Mars in particular?
I like Mars from two aspects. So we probably will. The scientific aspect is interesting, and more than likely, I think we'll find that life did exist there and maybe still in some corners somewhere. So in terms of just science, if we can get there and really investigate, that's big. But I am a believer in the what does Elon Musk call it? The sustain the light of consciousness. Why he's so interested in setting a colony on Mars. It really is not only to keep the human race growing, but also as an insurance policy. If the human race does have issues on Earth in the long term, if we have another viable place to live. And so I see it really as important for humanity, both to prevent us from stagnating, because we like to explore, we're curious, and to give us another foundation.
What do you think is the biggest barrier right now that you're seeing to getting one up? Is it cost or is it perceived risk? What's stopping it from going up tomorrow?
I'd say what's stopping it from going up tomorrow on Moon or Mars, the we're looking at a 10 kilowatt reactor. And a lot of people say, oh, we want, 40 or 100 or 1,000. And the problem is that we've seen for the last 40 years, and right now there's very few experts. There's a lot of people with degrees, right? And the unfortunate thing is that they can become experts in a world where there aren't any experts. It's kind of convoluted. So what happens is every program I've been on, we've kind of got it started with something. Here's something we can do, and somebody steps in and we can do something better. And so, and we're kind of best is the enemy of good enough kind of guys, or however that mantra goes. But somebody will come in and say, we can do that better. We can give you more power. We can make it lighter. And the customer, whether it's NASA or DOD, always bite. Because these guys say, look, we know what we're doing. And so they end up taking a bigger step than they can in these programs. And they ultimately fail. Every program is killed in reality just because they run out of money. They'll always use other excuses, but it costs more than they promised, it was going to cost, or took longer. And that's been the case in every space nuclear program and every terrestrial nuclear program today. So the biggest barrier is getting somebody to agree we need to do a simple demo. And we can do this for $100 million, which is a lot of money, but it's not like bank breaking in order to start gaining the expertise and capabilities by actually flying a reactor, because operating the reactor is the hard part. And so since we can get into the testing maybe next, because it's that the inability to test is really what makes it hard. And so we're kind of in a chicken and an egg scenario.
Can you elaborate on that a little bit and share some insights into the unique challenges of testing nuclear reactors in space? How does that differ from just a traditional reactor?
I mean, the good news, the first order challenge is testing any reactor on the Earth, right? Because nobody's still done it. We did it with Krusty. There hasn't been a new reactor tested by the United States, since the 70s, and then Krusty, right? So obviously it's challenging because it hasn't happened. And a lot of that is that we've made nuclear go to safety standards that are 10 to 100 times stronger than any other thing. I'm sure you've talked about that, how the fear of radiation has crippled reactors. I think we try to make nuclear 100 times safer than anything else just because everyone's so afraid of it. And so that's made the testing hard on the ground. And then the fact that we haven't, it's kind of snowballed in the fact that since we didn't do any testing in the 80s, we got dumber in the 90s and then the 2000s. And so that there hasn't been any testing, and even getting back at testing infrastructure is going to be hard. The good part for space reactors is we don't have to worry about a lot of the safety that people on Earth do. And so what we want to do is avoid testing on the ground, because it's harder to get approvals to test on the ground than it is to operate in space, because there's not going to be anybody around. And so that was our whole idea with DUFF and Krusty. If we can find a way to cheaply test this on the ground, we passed our biggest hurdle, because we have ground tested this thing, and why it's so far ahead of any other technology. In space, there's a lot of things that make your life harder, but one is you don't need the triple redundancy on safety because there's nobody nearby or there's no atmosphere to contaminate.
What steps are you and the SpaceNukes team taking to educate the public on safety and the benefits of space-based nuclear reactors?
What Pat and I do, we'll go to schools. I mean, I love going to local schools. All the ages are great. I tend to like the fourth to fifth graders the best. I'm trying to think, but we'll go to the elementary school, the junior high, and the high school, and we talk about how the Simpsons was misportrayed, but hopefully I think it's a parody. But Chernobyl, the HBO series Chernobyl, really, really exaggerated the effects of radiation by incredible amounts. And the problem is it was so well done and so enjoyable to watch that people really ate that stuff up. It was very egregious, but it makes it exciting, right? It sells. It's the fear of radiation sells, and they play the scary music. But when the guys were running out on the roof there, none of those guys didn't go beyond their standard dose limit. And they're playing scary music and they're running out there, on the roof. And same with the guys that went underneath. I'm going into the show that people might not have seen, but people going underneath like they're on a suicide mission, then they were fine, and the whole masks thing, and it was way overdone. And they perpetuated the risk that thousands or tens of thousands died. I mean, the data clearly shows it was less than 100, and all but 8 were people that went into the fire that were the first responders that clearly got a lot of damage. But there's been no evidence of latent cancer increase afterwards to any of the public.
I think it's really cool that you go talk to fourth and fifth graders, because I think space is such an interesting way to get the younger audience interested in nuclear. It's because it's such an interesting topic for them, and me too, but
it is. Yeah, and we had no shortage of interns applying to work with us. It's easy to get people excited, and that got me excited. And yeah, we can usually get our pick of the best engineers.
I have a side question, but have you ever wanted to go into space, or do you like being on the ground?
I would definitely like to go into space. I would go at any point. We always joke about making our reactor, so you do need an operator, to go. But the problem is that, the Kilopower reactors and the Krusty reactor, they're designed not to need an operator, right? That's part of the difficulty of space, right? Is you've got a time lag for communication. You can't really have a human in the loop for near-term control. And so we made these reactors as simple as possible, such that we don't even need a smart computer. These reactors, what we call, they self-regulate or they load follow. And it's really cool. This is what we showed with Krusty, but it operates like a thermostat. So we have what we call the control rod that controls the reactivity, the K effect of the system. And when that is in position, when the reactor is on, it wants to stay at the same temperature. That's the physics. And how that works is if it heats up, the atoms move further apart. It's really simple in terms of, it's more like a mechanical feedback than a nuclear feedback. But as it heats up, the atoms move further apart and more neutrons leak out and causes the power to go down, and vice versa. So if the temperature goes above 800 C, it will do what it needs to get back to 800 Celsius by reducing the power. And so no matter what you do to it, it's not going to overheat or underheat in the long term. It's going to have a small transient oscillation. So this is what's great. Even if we lose all our heat removal, which you might call a LOCA or whatever in a traditional power plant, the reactor doesn't if the temperature goes up a little bit for a short amount of time until the power goes down, and the reactor essentially shuts itself off by itself. And so we love this for a space reactor because we don't have the ability to control. You would also love it on Earth, but it takes a very small reactor to have this characteristic. You couldn't get megawatts in this fashion, which is what we need for power on the Earth. It's more limited in the tens to hundreds of kilowatts range.
What are some of the other differences when you're designing a reactor for space and perhaps environments like Mars or the moon versus traditional reactors that operate here on Earth?
The biggest one technically is what we call our heat sink, which is how you reject heat. And that comes back to what's called the Carnot cycle, which is the thermodynamic cycle. It's really the physics that gives us energy from heat, or useful energy. You need to have your reactor much hotter than the cold end. You have a hot end and a cold end. And on the Earth, we have a very good cold end that's like at the temperature of a river or the air. A cooling tower takes advantage of our atmosphere. Or you put yourself on a pond. And so you have a very good heat sink that you can effectively reject heat at between 0 and 30 degrees Celsius. But when you're in space, you have to use thermal radiation. You just have to get something so hot that it thermally radiates the heat away. And it's much harder when there's no air, to convect. And so we need to have our heat rejection or cold end at about 100 degrees C or 400 degrees Kelvin. And to be able to get electricity out efficiently, you have to have the hot end of your reactor at about 800 C or 1100 Kelvin. And that pushes you outside of all the reactors that are operating today. So you need high temperature technology. It's probably the biggest difference, besides not having the ability to control and having to make it light, obviously. I mean, the mass is a big deal, right? And that shielding becomes a real problem, because on Earth, we can just pour concrete, move dirt, and do shielding real easy. In space, we've got to take that with us, and it's a lot of mass. Unless, once we're on Mars, we talk about using the regolith of the soil, to make a berm, to make sandbags. You can even make concrete. Eventually we can use on the moon or Mars, use what we call in situ resources for shielding, or even just put yourself in a crater to protect people around. There's a lot you can do. But for the first missions, we just want to take all the shielding with us, which causes a lot of mass. So I think that's the three biggest differences.
What's the difference in exposure from the reactor versus space radiation?
The space radiation is, it's glorified. Well, I mean, vilified, a lot in most of the press. Generally, we shield our reactors. If you're talking a human mission, to where it provides, like 10 to 20% of the space radiation. I did a study where I tried to apply probabilities to all the things that can hurt or kill you. And, there's a lot. I mean, unfortunately, if you're going to Mars, there's a lot of steps that are going to be risky, right? That's the whole, exploration is always risky, right? But the radiation itself is a very small component of your risk. Even not having a hospital around is a bigger risk than radiation, right? Because here we take advantage. There's a hospital sitting next door, or the obvious one is you get a leak and you lose your atmosphere, your oxygen to breathe, right? Or you lose your power and you can't make new oxygen. Those are all much bigger risks than the radiation.
What's your dream outcome in all of this? Is it powering, scientific missions? Is it powering actual communities on Mars? Is it powering, space tourism? What's your ideal outcome?
I really like deep space missions like the Voyagers and the Galileos and Cassinis, going out and studying the outer planets. Especially, when it looks like Europa or Enceladus, really have signs of life. And so I get excited about those missions, which you can only do well with a reactor. Space tourism is cool just because it's getting us there towards being a spacefaring civilization. And then, but I think the power on Moon and Mars would be the biggest one, because I would like to see a sustained presence. I become realistic enough. As far as my lifetime is concerned, I want to see the first reactor in space. It's actually been 60 years now since the United States launched its only reactor. It's really a shame because it is such a great and useful technology, but we just can't get over the hump. And the hump is just doing something simple and starting. It's like, look at how SpaceX evolved. They didn't start with Starship. They didn't start with Falcon Heavy or even Falcon 9. They Falcon 1, a very simple system that they went and learned how to design, build, test, and launch a rocket. And they built the expertise. And now they've got Falcon 9 and Falcon Heavy just, working like gangbusters. And Starship's so hard that we'll see how they end up with that. And it's the same with any technology, right? Solar power has evolved. Automobiles have evolved, planes have evolved, and we need to do the same with this technology. We can't just design you the Battlestar Galactica, from day one. So we need to start simple.
Well, it sounds like there's a lot of potential excitement over the next couple of years, maybe as soon as 18 months, but over the next decade.
Yes. It's hard for me though, because, people have been talking about great nuclear things for the last 40 years, and we don't see them. So I guess I'm cynical now, which I hate to do to your audience and to you guys. But
no, but you're still here. You're still keeping on.
I'm going to work on this till I die for sure. There's no question about that. And so, but I'm more optimistic than I've been. Maybe right after the Krusty test, when NASA said they were going to fly it, but I'm almost back to that level of optimism that we're going to see a reactor in space, certainly in the next decade, and probably in the next 5 years, and hopefully in the next 2 years.
That's big.
Yeah.
That's so cool.
Okay, so last question. What book have you read lately that's worth sharing with us in the audience? Have you read anything great?
Well, the book that I read that really affected me a lot was Peter Thiel's 0 to 1. If you guys are familiar with that,
yeah.
It kind of tears down the economic model of competition and looks at more how innovation is best done by if you can dominate the space, kind of like as SpaceX has done. They're blowing away the competition. And they can innovate on their own schedule instead of having to nickel and dime for every contract. So I found that book very fascinating because it was not really what you expect and what you're taught, throughout your life, that competition is essential and good. it really depends what the market is, right? If selling widgets, then competition probably is. But if it's a brand new technology that's the first of a kind, maybe not. And so I would say that was the book that affected me the most.
That's a great recommendation. I haven't read it, but Peter Thiel he's jumping in on nuclear fuel, just announced in the last couple of weeks. So
yeah, he gets it. I mean, I think, and that he's another one that's big into long term of the humanity and human race, trying to do what's best for that.
Well, thank you so much for joining us. This has been so interesting. Nuclear and space are both such cool topics, and talking about them together is always super interesting. So thank you.
Thanks.
Thank you so much. The potential of nuclear energy in space is truly mind-blowing. Amazing interview with Dr. Poston today. Love his insights on the future of space exploration. And Mary, I think I'm going to keep a tally now of our space guests. Trudy said she did not want to go to space. David said he did. I still not really interested in it. What about you?
Yeah, I'm still a no. I definitely don't want to live on Mars.
Oh no, absolutely not. I don't even like to camp on Earth.
Same. Yeah.
So like a whole other planet I'm not all about that. I like to be here with access to, I don't know, not having to put some sort of apparatus on to go outside.
Mm-hmm.
Yet, at least.
Yet. Yeah, right. Maybe one day there'll be a 4 seasons on Mars, but until then, I think I'm keeping my feet on the ground and on Earth. I mean, it's like what we talked about earlier when Katy Perry came back from space, she like kissed the Earth. So,
yes,
I mean,
yes.
It is lovely to be on this planet.
I mean, did you see the meme though of Gail King walking onto the spacecraft? It's been like memed everywhere.
Yeah.
She was kind of looking like, I don't, and that's me. That would have been my expression.
Yeah, I mean, I can't even handle the intense space ride at Disney World. I mean, it's like the G's just crush you. I can't imagine doing that in real life. So I'm here for now, but it's not a no forever. If things
the
change,
4 seasons.
Yeah, exactly.
Yes.
Yes.
If there's a 4 seasons on Mars, we'll talk.
Yeah.
4 seasons, if you're listening.
Yeah.
We think this is a great idea to attract more people to want to go. Now's the time.
Mm-hmm.
And also we need our automated hair and makeup systems to go through, like the Jetsons.
Yeah, and it can be all powered by nuclear.
I love that. Powered by nuclear. Nuclear makes it happen.
Nuclear does make it happen.
Thank you so much for listening, and we'll see you next time.
Make sure to subscribe on Apple, Spotify, or wherever you listen to stay updated on all things visionary. See you next time.